but there's still even a bit of complexity in just kind of getting up to speed, installing all the right libraries and so forth. But a lot of that is packaged now in the PyPSA models. So it really went through a little bit of a process of understanding some of the basics, and luckily Python is really easy to get up to speed, and it doesn't take a lot of effort to at least be able to do some basic work. Then from there, the next step that we took was to start with PyPSA. So as Tom mentioned, PyPSA is sort of like the framework, and it's like gives you the tools in your toolbox, and then you build a model on top of that. So just understanding like what's the very basic functionality within PyPSA, and how you can kind of stitch a model together, even if it's kind of just starting to put a few generators, and there's really a great list of kind of examples where it's a Jupyter notebook, and then you can kind of run each block and see exactly kind of what some of these different functions are. So I think that's definitely a great place to start. It's quite hard to jump into a huge model if you kind of don't really understand just what the building blocks are doing. In the next step, so once we started to get comfortable with that, is then building our own models. And there's kind of two models that we initially focused on. So the one is like Rabia mentioned earlier, a sort of simplified dispatch model. We feed as much data as we can into that about what resources we think are coming online, how the existing plant is performing, and then really trying to gauge what is the risk of load shedding, and trying to highlight, okay, obviously it's not a crystal ball, but just trying to show that, okay, we're in the red zone, or things are improving with this suite of resources. The other thing that we've been doing more on the commercial side is doing a lot of energy planning studies for like large industrial clients. Also, where you're almost doing like kind of a mini RFP and helping them figure out internally what are the mix of resources that they should procure, what is the complexity around like the ESCOM tariff changes and how those change, and building all of that complexity into kind of a multi-horizon expansion model. So that's something that we use internally. And then I think once we got a decent grip on, now we built our own small, simple model, and then a little bit more complicated on the industrial energy planning. So when we started to toy around with jumping into the kind of bigger models. And there's a reason that we started with PyPSA-ZA. Obviously, the model existed for South Africa, and it's a little bit more of a streamed down model. In terms of it doesn't have all the functionality of PyPSA Europe or PyPSA Earth, but that also makes it a little bit easier to get started with. There's less scripts, there's less functions where something could go wrong, and you just spend a lot of time kind of chasing that. So we've started working in PyPSA-ZA now for a few months, and we're slowly starting to get into, now that we're actually modifying the code, getting involved a little bit more in the community, starting to be a little bit more active there, and hopefully maybe some of the modifications that we've done can filter through to PyPSA Earth. So just to give you an overview of the PyPSA-ZA model as it stands. So very happy to have Joanne here. She was part of the original authors of this model for this paper. And really what it is it's a single year model. So it runs full chronology for a single year, typically in 2040. And it's modeled at the level of the 27 ESCOM supply areas. So you can see an example of what the output of that model looks like. And really you can build resources kind of in two areas. So the one set of options, we're looking at the red zones, and the other is around power corridors and so on. So just to kind of take you through at sort of a very high level, okay, so this is the model, but what actually is the model? So essentially what it is it's just a series of Python scripts that essentially take your data, pre-process it, build a network model, which is essentially just equations that it's going to solve. And then it sends that to a solver. You get your answer, and then you post-process that data. So in terms of what some of the inputs are, because there's a lot of kind of higher spatial resolution, there's a lot of GIS data. So looking at sort of GIS shape files in terms of what are the supply regions that you want to model, where are the places that you want to put renewable resources. So in the existing model, if it's just grids or power corridors, what are some of the exclusion zones? So areas where you can't place renewables due to environmental exclusion, and then some aspects like population density and so forth. So essentially what the model does is it starts off and it runs a function where it tries to work out, well, it does work out what is the network topology. So that's really just what are the regions, where are they located, and what are the lines that connect them look like. Then it builds a base PyPSA network object where you kind of give all your kind of general parameters to the model. And then kind of where all the detail happens is you then go and attach generators to each one of those nodes. So those could be existing generators. So there's a script where it pulls in an Excel file with all the existing ESCOM generators. The original model only pulls in IPP generators that are conventional, so it doesn't pull in renewable IPPs. And storage, and then it also assigns load. So at the moment in the existing PyPSA-ZA model, that happens through kind of mapping what is the population density in the different areas, and then kind of sharing out the load between them. So now you've built your object, you have your generators attached. Now if you have to do any kind of pre-processing before you solve the model, so let's say you want to have custom constraints that you want to then impose on the model, it goes through that step. You then generate the file, send it to a solver, and get the results. So this becomes, obviously you can just kind of run each Python script, get the inputs, put it to the next Python script, run it. It becomes a bit clunky now to have a kind of a really big model and a lot of data. And now how do you know what you've run, what you haven't run? How do you get this data file? So and this is now true for all the PyPSA models, so PyPSA Europe, PyPSA Africa is essentially a workflow management tool called SnakeMake that you can use in Python. And essentially all that does is it's figuring out if you want an output file, so let's say you want to check how much renewable energy you can build in the red zones for a CO2 limit constraint. It will work backwards and find out, okay, what are all the input files that I need to generate to get there? Has anything changed since the last time I ran the model? Yes, let's say we made a change to the attached generator script, and then it will regenerate all those files, dependencies automatically, and it will solve the model without you kind of having to do that manually. So that just makes it a lot easier to kind of manage your workflow and keep track of which files need to be changed, which don't, and it just lands up being a single command line interface that you have to run. So what are some of the examples in terms of some of these data sets, what they look like? So this is a GIS data set on the left. So the different colors are essentially the land cover data set. So the model says, okay, only certain types of land cover like grasslands and so forth are available. Then the kind of exclusion zones from conservation and protected areas are now these kind of pink and orange. So you can't build in those zones. And now if you wanted to say, okay, we only want to build in the red zones, those would be kind of these dark green shapes. Or if you want to use land that's available along the power corridors, you could use either of those. And what the model will do is automatically say, okay, here we have our 27 supply areas. Within this supply area, we know that we have that much land available for renewable energy generators. So it's working out what is the potential in between all these areas. At the moment, in the existing PyPSA-ZA model, it doesn't solve for the renewable power profiles, the unitized power profiles. Instead, that is kind of already pre-processed based on CSR data. So it's just reading in a CSV file and then applying that resource across. In terms of how the demand gets split, this is then an open data set around population density, and then the demand gets kind of disaggregated according to that. So as I said, in terms of solar and wind resource data, this is based on the CSI solar wind aggregation study work that was done by Fraunhofer, and you see then the different capacity factors from that data set. So in terms of the kind of actual work that we've been doing to the model, our main goal is to have a tool that is comparable to the commercial codes that are used for the National Integrated Resource Plan. So we have a very specific end goal that we want something that is comparable and provides the same sort of functionality to how the DMRE and ESCOM do the RP. So a little bit of history on that is our RP is typically very low spatial resolution, so it's a single node model, essentially like a lumped capacity model, but then this multi-horizon intertemporal expansion. So when we looked at all the existing PyPSA models that were out there, they're focused typically on a single year's data and then a high spatial resolution. But a lot of the questions that we are grappling with in South Africa here are more transition questions and things like coal phase out and decommissioning, and for those you really need this multi-horizon expansion. So there's two ways that you can really do multi-horizon expansion, and it's kind of the one is termed perfect foresight and the other is a myopic transition path. So perfect foresight is really that you can see the optimization essentially runs all the periods at once. So it knows all the learning rates, it can see the entire period at once. Myopic, you really run one period at a time, and then you take those resources that are still in the grid and then you put them so they are now starting at the next period. So we are typically the Plexus way that is done at the moment. For the RP, it's all perfect foresight expansion. And luckily that functionality has recently been added to PyPSA. So we essentially started with, we took the base PyPSA-ZA model. We started, let's update all the functions. So any functions that have been updated in PyPSA Europe over the last 4 or 5 years, we took those, put them into the model. Then we started on, okay, what do we need to do to be able to run this multi-horizon expansion? And the first kind of hurdle is that it's going to be very computationally difficult to run 27 nodes with multi-horizon because the computational power increases sort of exponentially as you start adding more and more periods, especially with perfect foresight. So we then went about just adding some simplified functionality into the model that you can, just in the configuration file, you can set it for single node, so you just tell it South Africa and it will kind of collapse the whole model to a single node. We then worked on 10 supply areas, so very similar to what Ronak presented with essentially the 9 provinces, and kind of made a section for the hydro cluster just to kind of capture the grid properly. And then if you still wanted to do high resolution on the spatial side, you can leave the model as 27 supply areas. So that's kind of now a switch that you can choose which one of those you want to run. Then there was a lot of detail, like sort of very specific detail that we needed in the model that kind of wasn't there originally. And the first for us is kind of generator availability. So in the original model, sort of generators, there were no constraints in terms of how existing generators could run up or down. Kind of given the state of the ESCOM coal fleet, I think we really needed to try to capture that in the model to have a realistic idea. Obviously, wind and solar profiles are limited to more conventional generators. The second area that we've targeted was sort of spinning reserves, so your kind of fast-acting reserves, and then also slow-acting. And then because the model was originally done in 2017, a lot of kind of IPP capacity on wind and solar hadn't yet come onto the grid, but now subsequently there's significant capacity on that we kind of have to add into the model. So we take data from the IPP office and see where all these generators are located, and we feed those into the model. We've also worked on now integrating the multi-horizon expansion. So you can essentially either just tell the model to solve a single year, or you can send it as many years as you want, and it will then automatically flip into the multi-horizon expansion mode. We've sort of got to the point now that we're mostly happy with the code. It just needs to be cleaned up a little bit before we publish it. But now we start the actual hard work and really validating the code and checking the results against known results. So I think we'd be really interested to work with this group on kind of developing some standardized test cases where we can everyone can run it through their code, and we can kind of benchmark and see where the similarities and differences are. We also plan on using kind of the extensive work that was done by CSR as part of the RP to really share, because the input assumptions are shared, then kind of it provides us a very good test case against kind of the outputs that came from Plexos for those models. And then kind of future looking, obviously, it would be great to extend this further to look at sector coupled versions and all of hydrogen and heat and transport. So just in terms of kind of what some of these changes actually look like. So you can see here, this is based on ESCOM actual data for monthly availability. We have this now at a plant level, thanks to the kind of ESCOM really being open now with sharing data, which is great. So really capturing this kind of drop-in performance of the coal fleets and getting that into the model, as well as our kind of the challenges that we've had in the nuclear fleets over the last 3 or 4 years. And then even kind of your peaking assets, which typically obviously have a much higher availability, but sort of capturing that within the model as well. This is sort of the one area where Plexos kind of has a step up on PyPSA, in that they have a planned and unplanned maintenance scheduling that's built into the program. So you can kind of tell Plexos that it's you need to do so much percentage of planned maintenance, and then it will allocate that across the year. At the moment, we're just imposing the actual data, and then we can project that forward to say it's going to be the same, it's going to get better, it's going to get worse. But we definitely have an interest in possibly doing our own pre-optimization that does some of the maintenance scheduling down the line. So in terms of now, how do we do the grid representation? So this is based on the code from PyPSA-Earth. So we took PyPSA-Earth directly, and we ran the network model to kind of pre-generate what our network would look like. So on the left-hand side there, you see kind of the OpenStreetMap data representing kind of the network on 765 kV, 400 kV, 275, I think 200, and then 132 kV and below. Then what you see on the right is kind of this clustered network, sort of simplified representation of the network, where the thickness of the lines is then related to its installed capacity. If we look at then kind of the more simplified version of that, so we're going to go from the 27 nodes then down to the 9 nodes, or so 10 nodes. So what we've done is we've taken the Northern Cape province there, and we've just split it into 2 separate zones, so we can try maintain this kind of main artery of the transmission line through here. and this is now kind of the simplified version. So what I'm thinking is that because running the clustering and so forth lands up being kind of like another layer of complexity, we probably will provide these kind of pre-clustered networks to these shapes for the model. So we would kind of do that pre-processing and then include it. But obviously, kind of, if you wanted to generate your own shapes, then that functionality is available on the PyPSA-ZA model. On a similar scale, where before we were using the CSR solar wind data, and now we've started to integrate the AtLight module, so we can now figure out what the renewable profiles are in the different supply areas. So essentially what you can do is you provide AtLight your shape files, and then for whatever shapes you would like to investigate, you can then generate power profiles associated with those. So here's an example with the red zones, and then the kind of different power generation profiles that can come out of that. Again, this functionality is already fully integrated into PyPSA-ZA, so it's quite easy to kind of run it within PyPSA-ZA. Our thinking for now is that we'll probably again do the pre-processing and rather provide the kind of input files just to kind of, at least as a starting point, reduce some of the complexity. In terms of just capturing what generators come into the grid, so we've taken kind of the database of all the REAP projects, risk mitigation as well, and that is now becomes existing solar and wind data that gets fed into the model, and it gets assigned at the kind of closest region in terms of where it is located. So in terms of the kind of our overall goal of getting the multi-horizon working, in terms of functionality that we've modified, so all technology costs now can have learning curves moving forward. So instead of just a single Excel file with cost for a single year, you can supply multiple years of cost data, or you can keep the cost constant. Our config file allows for multiple years. If you want to run a lot of expansion periods, you can collapse the model to a single node. If you want to run full chronology, we've also kind of integrated the time series aggregation module, which is a separate Python library that allows you to drop your kind of resolution on your time series data. So instead of running all 8,760 hours in each period moving forward, you can run representative weeks or representative periods. The kind of last bit that we're working on is getting operating reserves and how that requirement for operating reserves will change over time. So ESCOM's kind of projecting this increase in operating reserves, so just incorporating that into the model. And at the moment, we haven't started kind of, as Ronak was talking about, the kind of planned expansions to the grid. So we kind of providing the grid network as is. And then when you run the optimization, it's determining kind of where it should do expansions. But we would like that we could force the grid expansions in a certain way moving forward. So that's kind of where we are so far. The model is kind of ready now for testing, but we don't want to show a whole lot of results until we've properly validated that and made sure that we're happy that there aren't any bugs. We will be providing this on GitHub, so we're already kind of in discussions to publish this to the PyPSA-ZA GitHub repository, so this model will be freely available. We obviously kind of want to help people get up to speed with it, and we'll try to answer as many questions, but kind of depending on what funding we can source to kind of provide those support services, that might be limited for now. But yes, so that's kind of where we've got to so far. Happy to take any questions.